Today we have Pasin Manurangsi. I hope I pronounced it right. He's a research scientist at Google, and he received his Ph.D. from UC Berkeley, where he was advised by Luca Trevisan and Professor Prasad Raghavendra. Um, he works on a variety of topics, including proving hardness to resolve for approximation, learning theory, and of course, differential privacy. Today, we will hear about his work on user-level differential private learning via correlated sampling. Yeah, so without further ado, I will let Pasin start. Thank you.
Thank you for the introduction, and thank you for having me here today. And I know that this is the day after the stock deadline, so thank you all for joining this talk as well. So this joint work with Buddy Gazi and Ravi Kumar, and the full paper is on arXiv if you want to read more, and it will also appear at New Rips this year. And please feel free to stop me at any point if you have any questions. So the specific setting of learning that we consider in this paper is pack learning. And this definition goes back to the 80s. In this setting, there is a concept class C, which is a set of functions from some domain X to binary values 0, 1 that we want to learn. There is an unknown distribution D, and our algorithm doesn't have an access to D directly. And here we assume that the distribution D is realizable, which means that there exists a function f from the concept class C, which again is unknown, such that for all x, y in the support of D, y is equals to fx. So there is a function f that completely realizes the distribution D. The algorithm access D through samples, and here we denote them by x1, y1, and so on to xm, ym. And once the learner or the algorithm sees this label sample, it needs to output a hypothesis. And here, of course, we want our hypothesis to be mostly correct. Specifically, we want the probability that hx is not equal to y when x and y is drawn from D to be at most some accuracy parameter alpha with pretty high probability. So throughout this talk, I will think of alpha as just a constant, and I will neglect the dependency on alpha just for simplicity here. And of course, this is a privacy seminar, so we want to do this start with differential privacy. And as you all know, in differential privacy, we want it so that our output distribution on neighboring data set x and x prime to be similar, and this is parameterized by two parameter epsilon and delta. The smaller they are, the more private our algorithm is. And as usual, we write epsilon dp as a shorthand for epsilon 0 dp. Now, of course, this doesn't completely specify differential privacy yet because we haven't said what are the neighboring data sets. And specifically, most of the, and in fact, I think all of the work in private pack learning previously consider the neighboring data sets that I would call item level neighbors. And this means that x and x prime are neighboring if they differ on a single example. So you add or remove a single label example. But this assumption is somewhat unrealistic because we are assuming, at least implicitly, that a user has only a single example or only a constant or small number of examples, because otherwise differential privacy wouldn't provide a meaningful or a very meaningful guarantee for a particular user. So this in this work we study a slightly different notion, which is the user level differential privacy, where each user can have multiple, where now there are n users, and each user receive multiple examples, again drawn from the same distribution D. And now the x and x prime are said to be neighboring if they differ by adding or removing a single user, which of course means that it can affect a lot of examples. As you might have already known, so there have been quite a fair bit of user level algorithms, especially learning lately. In fact, if I recall correctly, I think 3 of the last 4 talks of this seminar is on user level learning in some different notion of learning. But this work is specifically about pack learning. So this is a bit different from the previous 2 works that you might have heard about already. All right, so this is kind of the setting that we want. And we will consider, as usual, we will consider both the central model and the local model. So in the central model, we only need the output hypothesis to be differentially private. Whereas in the local model, we want to make sure that whatever each user send to the algorithm to the learner has to be differentially private. Okay, so before I describe the result, is the setting so far clear? Are there any questions? Okay, if not, I'm gonna continue. So we study 3 settings, right? So epsilon dp in the central and local model, and also approximate dp, the epsilon delta dp in the central model. And I'm gonna start with the last one. So yeah, so the middle column here is gonna be the new result. The column on the right will be the previously known results. So in the central dp in epsilon delta central dp, is known that you can learn with the number of samples, which is equals to polynomial in the little stone dimension of the concept class. Now, if you haven't seen little stone dimension before, it's not too important. It's a mistake bound in online learning, but we are not going to use it explicitly here. So it's not too important to fixate on the actual definition. And it's also known that a lower bound of log star little stone dimension is known. So in some sense, the little stone dimension characterize the learnability under epsilon delta dp, although the quantitative gap between the two is still fairly large. So our first result, we show that for user level learning, it's in fact possible to learn with the number of users that is completely independent of the concept class. In fact, the number of users that you need is only log of 1 over delta over epsilon. Although, of course, the number of samples per user will still have to depend on the concept class. And in this case, it will be polynomial in the little stone dimension over epsilon. And kind of unsurprisingly, we also show that the number of users here is necessary, even if you are given many and many more samples per user. Okay, so that's the first setting, the epsilon delta dp in the central model. So next we move on to the Pldp in the central model. Here it's known by Mill et al. That the sample complexity in the item level setting is exactly the probabilistic representation dimension divided by epsilon. So here, perhaps slightly disappointingly, we in the user level setting, we only show an upper bound that is similar to the item level setting. But I will note here that there is some difference. So it doesn't show up here because I'm not listing the dependency on alpha. But in the user level setting, our number of users doesn't depend on alpha, whereas in the item level setting, the number of samples has to depend on the accuracy parameter alpha. Yeah, so even though this upper bound of probabilistic representation dimension might seem large, it turns out that it's also tight using a similar proof to BML. And finally, we consider the local model. So in the local model, it's known that the sample complexity of the item level setting is a polynomial of the statistical query dimension divided by epsilon. And in this setting, perhaps surprisingly, we show that in user level, it's possible to learn using the number of users that only depend on the probabilistic representation dimension And the number of sample per user is also polynomial in probabilistic representation dimension. Now, of course, I haven't, if you haven't seen probabilistic representation dimension before, again, it's not too important. We are not going to use it explicitly here. But one thing I highlight here is that sometimes there is a very large gap, as large as exponential, between statistical query dimension and the probabilistic dimension. And one such case is the case of parity. So parity on D dimension, statistical query dimension is 2 to the order of D, whereas the probabilistic representation dimension is only D. So it's pretty interesting here that if each user only get one sample and you want to learn parity, you need exponential in the number of users. But if you allow each user to have poly in the samples, then you can actually learn using only just D over epsilon square users. So the total number of sample is still even polynomial in D, which is I find it to be somewhat interesting. And again, the lower bound on the number of users required from the central DP case also holds here. So the lower bound of probabilistic representation dimension on the number of users also. Okay, so those are kind of the main result. Yeah, go ahead, Salil.
Hi, Pasin. Sorry, I joined late, so I might have missed some important definition. But I'm a little confused about, let's say, look at the first row of your table. Why, like, if I have probabilistic representation dimension over epsilon users, can't I just take one of the samples from each user and then apply the item level algorithm?
Yes, that's right. So that algorithm would also work. Yeah, I think this is kind of the disadvantage of leaving out the dependency on alpha. So what happened is the following: in the item level setting, the number of samples has to depend also on the 1 over alpha, where alpha is the accuracy, the error in your learner. But in the user level, the O of probabilistic dimension divided by epsilon is actually doesn't depend on alpha. Yeah, so you can get a very accurate learner while the number of users doesn't grow, but of course the number of sample per user would grow.
I see, and maybe a better, like a result one would hope for there is just like poly 1 over alpha samples per user or something like that might be what you conjecture as the right upper bound.
Yeah, I'm not sure. I think that's a very interesting question, and that's one of the open questions that I'm gonna try to highlight at the end. But yeah, like I really don't know like what happens in between. Like, is there like a smooth trade-off, or is there like a drop-off cliff somewhere? Like, yeah, I think it's interesting.
Thanks.
Yeah, thank you for the question. Any more questions about the results? Okay, if not, I'm gonna describe some of the ideas, and yeah, and basically, Kobe, yeah, please.
Okay, hi, Pasan. So one question, isn't it the case that users have enough samples to solve the problems on their own, at least in the epsilon DP case?
Yeah. So actually, yes. So this is correct. Indeed, like as you will see in a moment, in our algorithm, each user does solve the problem on their own. But even if they solve their problem, there is still a question of agreement, right? How do all users agree to contribute to like to contribute to the same hypothesis, like in case that there is some ambiguity. And that's where the correlated sampling comes in. Yeah, but yeah, that's absolutely right. Yeah, I think it would be much more interesting to explore like this like middle regime where like each user can almost solve the problem on their own, but not yet, and then see what happens. Yeah, but in this work, is in this like a very extreme regime where the user have enough sample to solve the problem by themselves. Yeah. Okay. Okay, cool. Yeah, so then I'm gonna describe the
question.
yes.
Maybe you have to come near the microphone.
Sorry.
I just missed the definition of the SQ dimension. Could you please remind that one?
The definition of what?
Of the SQ dimension, yeah.
Oh, the SQ dimension. Yeah, the definition of SQ dimension is, I mean, roughly speaking, is the number of statistical query that you need to learn the concept class. Yeah, but like a more precise definition is like the log of the number of functions in your class that are uncorrelated, like uncorrelated in the sense that the dot product are close to zero.
The number of the static queries, like.
Can you repeat that again? Sorry.
Is it the number of the static queries? Okay.
Yes. It is the number of the statistical queries. Yeah.
Thanks.
Okay. So any more questions before we go to one of the algorithms? Okay. If not, I'm gonna continue. But yeah, please feel free to stop me if anything is unclear. Yeah, like some of these definition, I kind of didn't define it because we are not using it explicitly, which is why I'm kind of skipping some of these definition. Yeah, sorry about that. Okay, so in all the three algorithms, we will use the differentially private selection as a subroutine, and I'm sure most of you are pretty familiar with this, but just to recall, in differentially private selection, each user I holds some xi from some domain. Here I'm using B to denote the domain size, and and the algorithm wants to output basically a frequent element. And the guarantee that you can get here, like this is one of the guarantee you can get here, is that if there is an element that appears, say, tau times, then with probability 0.9, you will output an element that appears tau over 2 times. And this is a very well studied problem in literature, and the value of tau is well known. And each of these value of tau will indeed determine the number of users that will be needed in our algorithms. And I will start with the approximate DP, which I will spend most of the rest of the talk on, and I will comment a little bit on the Pldp algorithms later on in the talk. Okay, so for approximate DP, for differentially private selection, is known that you can get such a guarantee, you can discover such a frequent element as long as you are the element appears something like log 1 over delta over epsilon times. And this indeed will be the number of users that we get in this central DP case. So yeah, just to remind you, we want to get this number of user, and the sample per user that we want is polynomial in little stone dimension over epsilon. And a crucial notion that we'll be using here is a notion of globally stable learner, which for most of this talk, I'm gonna just call it a stable learner just for brevity. And what does the stable learner means? So a learner is stable basically means that if you fix the distribution D, then on most draws of these M examples, you're gonna output the same hypothesis. So more precisely, you say that a learner is beta stable if there is a hypothesis H star that is output with probability at least beta. And here in 2R, I'm assuming that hypothesis H star has small error, just for simplicity, so that we don't have to worry about both the error term and the stability. So yeah, so from now on, we are gonna not worry about the accuracy. Okay, so this stable learner means that if you run this algorithm many times on many different draws of the samples, you will still get one of the hypotheses like this H star with probability at least beta. Okay, so Ban et al. Shows that you can use a stable learner to get a differentially private learner in even in the item level setting. And here I'm just gonna translate the reduction to the user level setting and see what happens. Okay, so the kind of probably the most natural way to translate the learner in this setting is as follows. So you just let each user I run such a stable learner to get a hypothesis HI, right? As we stated earlier, we expect many of these HI to be equal to H star, the one that has the most probability. And then we'll just run the DP selection, right? So if H star appears many times, we should be able to recover it at the very end. Okay, so this looks great, right? But of course it shouldn't work as is. Otherwise, we wouldn't be writing this paper. So what goes wrong here? Well, let's take a look at the number of users that will be required under this algorithm. So recall that we use tau to denote the threshold that we need for the selection algorithm to succeed, and beta to denote the stability parameter. Since we need to see the H star tau times and H star only appear with probability beta, it means that we need roughly tau over beta users for this to succeed. But the best known stable learner, which is from Ban et al. Paper, has beta that is only exponential in minus of the order of little stone dimension. So it is 1 over exponential in little stone dimension. But since the number of the number of users, we require grows with 1 over beta, this means that the number of users we require will grow with exponential in the little stone dimension. And this is not what we promise, because we want the number of users to be constant. I mean, to be log 1 over delta over epsilon, regardless of the class. Okay, so this is kind of the first attempt at translating directly what is known from the item level setting to the user level setting. It kind of works, but it doesn't give exactly the result that we want yet.
There is a question in the in chat.
Oh yeah.
Sorry, it was from a few minutes ago. I didn't want to interrupt you.
Oh, so how do I see this question?
Yeah, so let me read it. Is the dependence on epsilon in the number of samples per user necessary? Is it known that this task is impossible with the number of users you specify, but poly little stone dimension samples for example?
Oh, yeah, I'm not sure. I don't think it's known. Yeah, I don't think it's known. Yeah. So just to be clear, the number of example per user that we give may not be tied, and it's very much possible that this can be reduced. Yeah.
But it must depend on epsilon, right? This is for the local model.
I mean the number of yes, but that could be only in the number of users, right? It doesn't have to be in the number of samples per user. Yeah, but I mean, either the number of users or the number of sample per user has to depend on 1 over epsilon. Yes, but
okay.
Okay.
You've got another question?
Yes.
Is another problem with this, other than the number of users, that the selection is only guaranteed to find some hypothesis that occurs at least t over 2 times, and it need not be H star?
Yeah. So this is something that we have to work a little bit in the paper, but I'm kind of ignoring this like this accuracy concern here. But basically, yes, you do still need to make sure that the output hypothesis has good accuracy. But actually, this is not that hard to guarantee because you know your learner typically will output a hypothesis with good accuracy with high probability, and anyway, so yeah, your selection algorithm, even though it doesn't output H star, it will output something else that is also a good answer.
Okay, great. Thanks.
Okay, so any more questions before we see how to reduce the number of users?
I just I think I missed this. So here we have access to better stable learner, and we also want to provide a differential private better stable learner. Is that?
Oh, okay. So
right?
sorry. So this is my bad. Okay, I should have stressed this, but the notion of stable learner has nothing to do with privacy. So the notion of stable learner it's just about the learner itself. It's not about the privacy at all. It's just about stability. And indeed, the stable learner that was given in Barnett et al. Is not private. So in particular, in this diagram here, the stable learner that you run on each user is not private. It's just some learner that is stable, but it doesn't have to be private. The privacy comes from the fact that you are running differentially private selection on top of the output of the learners, and that's how you get the user level privacy.
So is it trivial that the stability will basically remain unchanged? Because I mean, or I mean, do you need to do some extra work to basically preserve the stability?
Oh, sorry. Can you do you mean the stability of the entire algorithm, or do you mean something else?
The entire algorithm, like the
final
the
entire algorithm.
H that you're outputting.
Yeah, sorry. I was thinking about something else. If the question is whether the final algorithm is stable, I'm not sure. Like I think it should be true that it's somewhat stable. I'm not sure whether the stable parameter will decrease a little bit. Yeah, but that's not something that we analyze, I think.
I see. Okay, so so you don't have to have the final output to be stable. It could be stable with parameter better, or it could be not. So the point is that we want the edge to be just private. Is that?
Yes, that's right. Yes. So we only use the stable learner as a subroutine, but the final algorithm that we construct, the main claim is that it's private. Yeah, it's user level private.
Okay, thanks.
Okay, cool. Okay, so we have seen this attempt which works, but it doesn't give us the number of users that we want. So let's try to reduce the number of users. And we reduce it by extending the notion of stable learner to what we will call a pseudo stable learner. So the definition is almost the same as before, except that now the learner gets an access to some shared randomness R. And we say that a learner is a pseudo stable if, roughly speaking, if once the shared randomness is fixed, it becomes stable. Okay, so yeah, so more precisely, we say that it's a beta alpha pseudo stable if with probability alpha over the randomness R, it outputs some hypothesis H with probability at least beta. But this hypothesis H, I write here as HR to stress the fact that it can depend on R. So once you fix R, it should be stable. Okay, so everything is exactly the same as before, except that you have a shared randomness. and now your H star now can depend on the R.
A question?
Yeah.
Who is the randomness shared among? Like, what do you mean? Who's
Yes,
sharing
so
the randomness?
this is a good point. So let me actually go through the next slide, and it's going to be clear here. So we are going to share this randomness among the users. Okay, so the user, instead of running the stable learner, they will run the pseudo stable learner with the same share randomness R. And this will give them H1 to Hn, like very similar to before. And then you can run DP selection similar to before again. Okay, so far everything looks exactly the same as like 2 slides ago. So what is going on here? The only gain that we are getting here is that we show that it's actually possible to get a pseudo stable algorithm, a pseudo stable learner with stability parameter that is constant, and in fact you can get this constant arbitrarily close to 1, like 0.9999, instead of before where it was 1 over exponential in the little stone dimension, right? And since this stability parameter is now constant, recall that the number of users that is required is tau over the beta, the stability parameter, but now beta is constant. So the number of users that is required is now only the tau, the required threshold from the selection. And this indeed gives you the number of users that is log of 1 over delta over epsilon. Right. I mean, of course, I haven't told you how we get a pseudo stable algorithm with constant stability, and I'm gonna do that next. But does this like revised algorithm make sense? Or are there any questions about this this like use of shared randomness, or like the modification in general so far?
What's the parameters for pseudo stable again? What do they mean?
Yes. So okay, sorry, let me go back. So there are 2 parameters. There is the beta, which is again the stability. So this is your stability, the probability that you output like this special hypothesis. And there is also alpha, the probability that you fail over the probability that you succeed over the share randomness R. Yeah, but here the alpha, you can think of it as like a constant. It doesn't matter too much for the remainder of this discussion. So mostly beta is the parameter that we care the most about.
And it's alpha that you can push arbitrarily close to 1, or a constant.
Yeah, good question. So we can actually push both alpha and beta arbitrarily close to 1. Yeah, so any additional questions?
I think I have a small question on the setup, in the sense like we're still in the central model, and so this randomness is from the central DP algorithm. The central DP algorithm picks the randomness, gives it to the. Okay, let's see. Yeah.
Yes.
I think. Thank you.
Yeah. So in the central model, indeed, like all these like sub learner that are run, like it's just the central simulating these learners, and the shared randomness indeed the curator is the one who sample this randomness. In the local model, we do need this like public share randomness R, and currently we don't know how to get rid of it, and that's one of the open questions that I think is pretty interesting.
I see. Thank you very much.
Okay, yeah. So so I guess I'm gonna continue and then tell you about how we get such a pseudo stable learner with stability that is pretty large, a constant instead of sub-constant. And okay, and this brings me to the second part of the title, which is correlated sampling. So just to, like, many of you might have also seen correlated sampling before, but just to remind you, in the correlated sampling setting, there are 2 parties, and each party holds two distribution mu and mu prime. If you haven't seen it before, you can think of mu and mu prime as like distribution that are close in the total variation distance, but are not exactly the same. And what do they want? So they want to sample elements. Player 1 want to sample an element from mu. Player 2 want to sample an element from mu prime. But they want to sample it so that their elements are equal with a pretty large probability. And specifically, if you don't have shared randomness, this is impossible. So here you indeed need a shared randomness. And on this shared randomness, player 1 will sample u and player 2 sample u prime. And what you want, and the guarantees, there are two guarantees of the correlated sampling here. One is that each u and u prime have the correct marginal. Specifically, the distribution of u is exactly mu. The distribution of u prime is exactly mu prime. And that they disagree with very small probability. Specifically, the probability over the shared randomness that they disagree is at most order of the total variation distance of the two distributions. So the closer the two distributions are, the smaller this error is. And again, in this talk, we are not gonna use this. I like open this up. We are gonna use this completely in a black box manner. But if you haven't seen it, the correlated sampling before, is basically some sort of min hash. So if you have seen min hash before, this is something like min hash. Okay, so is there any questions so far about the correlated sampling? Okay. Now we're gonna see how to use correlated sampling to build a pseudo stable learner. Okay, and the high level idea is pretty simple, right? You take your input label samples x1, y1 to xm, ym. You build some probability distribution mu on the hypothesis, and you hope that this mu this mu is close, for most of the draws of the samples. And if that's true, then you can just use the shared randomness and the correlated sampling to output the H, right? Now, if you plug in exactly just the guarantee of the correlated sampling, you see that if mu doesn't change too much across most of the random draws of the xi, then you indeed immediately get the pseudo stable learners. Okay, yeah, I'm not gonna go into the details of the parameter here, but that's basically the idea. So you want your probability mu to be roughly the same for most of x1, y1 to xm, ym drawn from D. If you can do this, you are done. But how do you construct this mu? And this is what we are gonna go next. And the answer is indeed you do some sort of boosting of the stability from the stable learner, which itself doesn't have a very high stability. Okay, so how do we do that? Well, again, we are gonna run a bunch of stable learners, and then try to use them to construct this probability distribution mu. Okay, so what this means is that we will divide our input sample into batches. I'm calling the batch B here. And then you're gonna run your stable learner to get H1 and so on to HB. And okay, and then what could be the mu, right? A first attempt would be to let mu to be the empirical distribution on these HIs. This and just to recall from the previous slide, the purpose of this mu is you use the correlated sampling strategy to sample the output H from mu, right? So it turns out that this doesn't work yet. So why is that? Well, first of all, if you have recall that the stable learner has a pretty low stability beta here. And if we just take the empirical distribution, this doesn't really solve the issue because again, like the HI with highest probability can still have a probability of beta in the empirical distribution. And moreover, the mu can actually change a lot if you change your distribution. I mean, specifically if your stable learner is really weird and it output this H star probability beta and otherwise it output completely random hypothesis, then actually if you run this multiple times, your total variation distance is going to be very large. So this is not good enough for us. So how do we fix this? So we fix this by doing some sort of weighting so that a hypothesis that appears many times get a lot of weights, and we just do exponential weighting. So basically we set the probability mass of HI to be proportional to exponential of some parameter gamma times the frequency of HI. So the number of times that HI appear across these batches. And then again, just to recall, this mu is then used in correlated sampling to get the final output H. Now, yeah. So we are not going to do any computation here, but roughly speaking, this strategy works. You have to set your gamma, the weight in the exponent, to be roughly 1 over beta, and you have to set the number of batches to be roughly 1 over beta square, and you can show that mu and mu prime are close most of the time. I mean most of the time among the randomness of the x1 to xm, x1 y1 to xm y.
I have a question. Isn't beta like 1 over exponential Littlestone dimension?
Exactly. Yes. So this is a good point. Yes. So yeah. So Albert indeed point out the right thing. So actually let me skip to that slide first, and then we can yeah, if we have time we can come back to the slide in between later. I think is of less important. Okay, give me just 1 second. My presentation is a bit slow. Okay, so what Albert is asking is the following, right? So I was telling you previously that we are gonna set the number of batches to be 1 over beta square, right? But how does this number of batches affect your sample complexity? Recall that you have to run your stable learner B times, where B is the number of batches. So your sample complexity will blow up with B, which is now 1 over beta square. But recall that the stable learner that we start with only have beta that is 1 over exponential in Littlestone dimension. So actually this approach also wouldn't work yet, because it means that the sample complexity that you need per user will be exponential in the Littlestone dimension. So just to quickly note here, there are 2 things here, right? The number of users and the number of samples per user. So the approach that we are staring at is fine in terms of the number of users, because we get the pseudo stability that we want. So we do get log 1 over delta over epsilon users. But the sample of user is too large because the B that we are selecting is too large. So each user now use exponential in Littlestone dimension instead of just polynomial that we claimed earlier. So indeed we're gonna have to fix this. And the way we fix this is we are gonna use yet another extension of the stable learner, but this time not extending through the use of public randomness, but through the fact that you allow the learner to output a list of a certain size, and here we call it a list stable learner. So the setting is very similar to before, except that you say that yeah, a learner is a L beta list stable if it output a list of size L, and the list contains some H star with probability beta. Okay, so now you're more relaxed, right? So you're allowed to output a fairly large list. It just have to contain the hypothesis H star that you want, right? So this is more relaxed compared to the standard stable learner. And it turns out that so in our paper like this year, we show that it's possible to get such a list stable learner where list size is exponential in the little stone dimension, but with the stability parameter beta that is 1 over polynomial in the little stone dimension instead of 1 over exponential in the little stone dimension. Okay, and once you have this list globally, list stable learner, you can plug it in like exactly the same as before, except that now instead of having one hypothesis from each batch, you just have a bunch of lists from the batches, but you can define mu in exactly the same way as before and so on. And the point here is that the dependency on the batch size is only log of, the dependency on the list size is only log of L, it's not polynomial of L. But since our list size, even though it's large, is exponential in polynomial little stone dimension. So its log is fine for us. It's a polynomial in little stone dimension. So indeed, this is the final modification that we need to get the sample complexity that is polynomial in the little stone dimension. Okay, yeah, I'm not sure whether I went too fast in the last like 10 minutes or so, but this is basically like the entire algorithm for the case of epsilon delta dp. That there is nothing hidden here, just calculations.
So I have a question.
Yes.
So when you make the mu distribution on HI proportional to the exponential in the frequency, sorry, I missed that part. What was the reason behind it?
Oh yeah, the reason behind it is that you want to weight something that appears more time more aggressively, right? Because I think suppose that you have just one H that appears like with probability beta, right? If you don't do any weighting, that H would still, like if you just use the empirical distribution, that particular H star is gonna still get a weight, like it's gonna still get a probability mass of roughly beta in mu, right? But that's too small. We want that to be larger, and that's why we are weighting. But also this weight helps kill out kind of the mass, the irrelevant mass, in some sense, because just think about, think about the case where you have H star that is output with probability beta, but with probability 1 minus beta, your learner completely output like completely random things, right? In this case, like the empirical distribution can be very large. If you don't weight this H star, so you have to weight this H star so that the most of the mass is now given to H star, and then the remaining has like almost zero mass in some sense. Yeah, but this is just one weighting. Like I would suspect that some other some other weighting would work as well. I don't see any particular reason why exponential weights is the only way to go.
Right, because I was also like thinking that why not just use some kind of a linear weighting thing? So I'm sure, like, I don't know if you tried that or something, but like, wouldn't something simpler work here?
Yeah, I think it is totally possible. Yeah, it's just that I think it was easier to analyze the exponential weighting, and that's kind of that's how we go with it. But yeah, I wouldn't be surprised if there are simpler weightings that works here, and maybe it also give a better parameter and dependency in general.
I see. Thank you.
And any additional questions?
Can you give context again? Like, so like poly lowest on dimension, how does that compare with like central and item level?
Yeah. So central item level, yeah, the best known, I mean the best known generic learner also requires poly in the little stone dimension. But for some concept class, there are much better things that are known. Like for example, like thresholds, right? So threshold log star like to the 1/2 is known. Sorry, to the 1.5 is known, which is much lower. And this gap, I mean, yeah, even in the standard item level central setting, this gap has not been closed yet.
Right, but like I guess kind of going back to what Kobe mentioned before, if you're allowing this many samples per user, what's stopping each user from like learning, and like we just resort to so we designate one user to learn and then you just listen to that user. Yeah,
but if okay, yeah, I think that this is kind of the point, right? Even if one user can learn a good hypothesis, right?
Right.
You still cannot output that hypothesis privately.
Oh, I see. Sure. I see. Okay, so you're saying the sample complexity is poly lowest in dimension, but it's done non-privately. So the aggregation you do is, I see. Okay.
Yeah, I mean, if you talk about like completely like not non-private setting, it would just be like just the VC dimension. But
right.
But it has exactly this problem. Like even if you have a good hypothesis class, you cannot output, and that's why you have we have to do all this work so that like all the users kind of agree on the same hypothesis, which we can then output.
Right. Okay. Thanks.
Salil?
Yeah, really interesting results. I wonder if you could talk a little bit about the model of like, are there scenarios where you expect that, where we can imagine where you have like privacy concerns, but each user has many independent draws from the same distribution, but we need user level privacy? Like normally if I'm thinking of privacy in a, like, if what a user is contributing is data about themselves, then it wouldn't be all like independent draws from the same distribution that other users are drawing from.
Yeah, that's right. Yeah, I think this is like the question of when the data is homogeneous. I think is interesting. Like, yeah, I mean, like, to be clear, I do think that the heterogeneous case is much more realistic. Yeah, but I guess we study the homogeneous case as like a starting point. But you are right. Yeah, I think the heterogeneous case is much more realistic for like practical applications.
Thanks.
Yeah. So if there is no question, if there is no question, I'm gonna conclude a little bit and maybe just talk about a couple of open questions. I'm gonna skip the Pldp. It's not that hard. It's pretty similar. You just construct the mu slightly differently. It's nothing too complicated. Okay, so in summary, we give the user level DP learning algorithm in the pack model. We give nearly type bound for the number of users in each of the local and central model. And the main idea is to use pseudo-stable learner in correlated sampling. And specifically for central DP with approximate DP, we get the number of users that is independent of the hypothesis class. I'd also extend to shuffle DP because we only require selection, and selection in shuffle DP for log 1 over delta over epsilon is also possible. For local DP, as I stated earlier, it even reduced the total number of samples in some cases, such as parity from exponential in D to poly in B. One thing I didn't talk about at all is the efficiency of the learner. In general, these learners are not efficient because you have to build this like a probability distribution over many hypotheses. But if you have an efficient SQ learner, then we also give a translation to an efficient user level DP learner. And the idea is to use correlated sampling again, but just to agree on the output of each statistical query. So basically make sure that everyone round their answer to statistical query in the same way. Yeah, so those are our main contribution. So two open questions. So this first one, yeah, this is one of the first question in this talk, is the question about the trade-off between the number of sample per user and the number of users. So previous work restrict the number of sample per user to 1 and then ask what's the mean number of users. In our work, we just assume that the sample per user is very large, right? As I said earlier, large enough that each user can completely learn the model. And then we just ask, what's the minimum number of users? So the question here is what happens in between, right? And yeah, I'm not sure how hard it would be to consider the general concept classes, but even for some specific concept classes, there are interesting questions to be asked. Like for example, again, in the parity setting, you have on the one hand, 1 sample per user and 2 to the D users, and like poly D sample per user. This one is a typo, and the number of users. So the question here would be what happened in between? Is there like a smoother trade-off? Is there kind of a cliff drop off here? It's a little bit unclear. The second question is also about whether this shared randomness is necessary. So we rely on correlated sampling, and correlated sampling by nature use shared randomness. And yeah, and I think there are multiple ways to formulate this problem. A couple of ways to formulate this, it would be like, first would be to ask the question directly in the local DP setting, whether we can get a similar result in local DP if we do not allow shared randomness, right? If we only allow private randomness, and this we don't know. And yeah, and another way to formulate the problem is to ask whether you need this notion of pseudo stability at all. Maybe just stability itself is enough. Maybe the first reduction that I show you is already enough to get the result in this paper. If that's the case, then you just have to prove a stronger stability bound for stable learners. And here, ideally, you would want the stability to be constant regardless of the class itself. So these two are a way to formulate this problem. Okay, so there are some cases where we know that this is needed, but this is not exactly the case on the left, so I'm not gonna mention it here. Yeah, and that's it for my talk. Thank you very much for your attention.
Any questions?
Thanks, Pasin. This was really cool. I have a question about this correlated sampling thing. Like, I noticed that you have that the total variation distance you want, or you want it to be, you want it to be less than or equal to 2 times the total variation distance, right?
Yes.
If you had unlimited amounts of randomness, then you could just do equal to the TV distance, right? By coupling. Is my understanding correct?
No. So actually,
No.
okay. So actually, this is a good question. So there is a paper that shows that 2 is the best possible. I think this paper is by, I mean, yeah, I know that Buddy and British are 2 of the authors. I can't remember who are the other 2. Yeah, but it's known that 2 is the best possible. And okay, and why does coupling not work?
Can you go back to the definition just so that we can make sure I understand it? And yeah, I'm curious how this is different from coupling.
Yeah. So, by the way, the two come from like your missing mass, like you're like missing mass and you're like exceeding mass. So
Okay, interesting. Maybe I might need to just think about it more. Thanks.
I have perhaps a simpler question on this slide, which is like that there's no communication going on here. So like
yes.
the player one doesn't need to know what mu prime is. Is that right?
Exactly. Yeah. So the player one strategy is completely oblivious to mu prime.
Oh, so the shared randomness is being introduced by like some external source, but it's not like player one's randomness is being used by player two in some sense. So it's not like a coupling as like Gautam was talking about. Is that correct?
Yeah, I mean this is correct, but it also seems, yeah, but now that you say it this way, it also seems weird. Yeah, I'm not sure. Okay, so what would be the difference between the randomness being from player one or from the external source?
I'm sorry.
What would be the difference between the randomness coming from player one and coming from the external source?
I was just like thinking in terms of like the algorithm, which is doing the correlated sampling, is generating the random coins, and those are being like, in some sense, shared. But like, in the other case where we're constructing some kind of a joint distribution between player one and player two, like player one's randomness gets used directly by player two, like in a coupling kind of sense.
I see.
So I'm looking. Are we? Yeah. I'm looking at the paper. The paper is called "Optimality of Correlated Sampling Strategies" by Pasin and British and a bunch of other people. And I haven't parsed it yet, but not every coupling strategy induces a correlated sampling strategy. Correlated sampling is a strict restriction of coupling. Somehow. It's not about computation. It's not about the length of the random.
Yeah, I think it might be from the fact that correlated sampling has to work for every mu, regardless of mu prime. Maybe, yeah.
Because with coupling, like the way to do this would be like mu prime would like see the output from mu and then can decide whether or not to sample fresh. But we don't allow that here.
No, yeah. Here the two player cannot see the other's output.
Thank you.
Cool. Thanks.
There's a question in the chat.
Oh, there's a question in the chat.
So let me read that question. If you had omega-1 stable learners for every online learnable class, wouldn't that imply impossible sample complexity results for private pack learning in the global item level setting?
From which paper? Sorry.
I mean, it didn't say any paper, but let me repeat the question. If you had omega-1 stable learners for every, I don't know, I thought that having larger, better.
Oh, yeah. Okay, so that is a good question. So, okay, so an omega-1, I was referring to an omega-1 stable learner, but I didn't say anything about sample complexity. So this omega-1 stable learner could have a very large sample complexity, right? And if it has very large sample complexity, it wouldn't contradict with like the lower bound of like log star of the little stone dimension. If I understand the question correctly.
Yes, it seems like the person is thanking. I think Sasha is thanking you for your answer. Thank you.
Okay, thanks.
Any other questions? Okay, let's thank the thing one more time, and we can go to lunch.
Thank you very much.
Thank you for the great talk. Let us know if you visit Boston, and we would be happy to have you at BU. Yeah. Thank you. Have a good day, everyone. Bye-bye.
Thank you.